So we have another parallel linkage right here. We want to find the force in bar BC. We're going to have to do this in 7 steps. And the first step is to notice that the velocity at endpoint A is perfectly horizontal, as well as the velocity in endpoint B. You should also notice that VA in magnitude, in this case also direction, is equal to VB. And they're all traveling in the horizontal direction. Why? Because if you think of this intuitively, bar AB is a rigid bar. If A is greater than B and they're all going in the horizontal direction, what does that mean? It means the bar is getting squished. So instead of being 300 millimeters long, it'll go to like 290 something. Since we know it's rigid, the speeds must be the same. Okay, now we can start our formal analysis. The first step we're going to do is to find the velocity in A and B, which are the same direction and the same magnitude. So we know VA as a vector is equal to omega of O cross product R of A from O, and that is equal to velocity of B as a vector as well. From givens, we know that this is 2 in the k direction, radians per second, cross negative 0.1 in the j, because the vector go from O down to A, perfectly horizontal, vertical. So do the cross product and you get 0.2 in the I direction, meters per second, and that is also equal to VB. So now step 1, let's move on. Step 2, we want to find omega CB. That is the angular velocity of bar BC. I can probably flip those two. Okay. What this is equal to is we have to start from VB. The definition of VB is omega of BC cross R B from C. Okay, now it's not very intuitive that we just move this to the other side because it's a cross product, but what we can do intuitively is know that since VB is going to the right, it's going to cause a rotation counterclockwise about C because C is pinned. So I'm going to drop all directions. I'm going to say 0.2 meters per second is VB divided by RB from C, which is 200 millimeters. That's 0.2 meters. And that is equal to the magnitude of C of omega BC. And omega BC has a magnitude of 1 radians per second. If I put the vector sign back to it, it will simply be 1 or just a vector k radians per second. So that was our step 2. Step 3, we want to find the angular velocity of the target bar, bar AB, and I'm going to assume it's going to go that way, which we'll see. So the way to find this is to actually notice the two endpoints are traveling in the same direction with the same magnitude. So let's draw over here. First, let me label step 3. Draw a bar. We'll call that A and B. Let me bring back a color, orange. And this is the velocity of A. That's the velocity of B. Didn't format correctly. Okay. Now what we want to notice is that the normal direction of these two vectors, because they belong to the same rigid body, are parallel. This means they do not cross. And if they don't cross, there is no instantaneous of zero velocity. So we can say note the normal of VA and the normal of VB are parallel. So instantaneous center of zero velocity doesn't exist, which means the radius of, say, somewhere A from IC is equal to infinity. Now we can say that the velocity of A is equal to omega of AB cross R of A from IC, which is infinity. And we can say that omega AB is 0. Or you don't have to do all these steps, and you can straight up say that omega AB is 0 because the instantaneous velocity doesn't exist. Right, that looks like 11, but it's actually parallel. Okay. Cool. So that was step 3. And I notice my color has changed, so let me switch back to my palish white. So step 4, this is where the math actually comes in. We're going to find the acceleration of A with respect to the system, or nothing, or we'll call it the absolute acceleration, and that is equal to alpha of O as a vector cross R of A from O minus omega O squared as a scalar multiply R from O, R of A from O. And this is given, if you look up, that is 4 in the K direction because it's spinning counterclockwise, I believe. Let's double check that. Yeah, it's 4. From O to A, it will be perfectly downwards, so negative 0.1 in the J direction. That was also given. That is just 2 radians per second, and this is repeated. So we'll plug in the numbers. We'll say 4 in the K cross negative 0.1 in the J minus 2 squared multiply negative 0.1 to the J. Do the math and you will get 0.4 in the I direction plus 0.4 in the J direction is equal to the acceleration of A absolute. Okay, that was our step 4. Our step 5 will be very similar, because step 5 we're going to find the acceleration of B absolute, and that will be equal to alpha BC as a vector cross R 2B from C minus omega BC squared scalar multiply R as a vector 2B from C. Now we have some unknowns in here, and that's okay, because step 6 we're going to create another set of equations, and it will end up being 2 equations and 2 unknown. We'll solve all the variables and plug that into step 7, which ends the question. So we know that acceleration of B is the magnitude of the angular acceleration of BC in the K direction by assumption cross negative 0.2 in the J direction because it's pointing vertically downwards minus, now I don't know what the Did I calculate that in step 2? Yes, I did. Omega of BC is 1. So I'm say 1 squared multiplied by negative 0.2 in the j direction. And I will get a vector AB is equal to 0.2 times alpha BC's magnitude in the I direction plus 0.2 j in the j direction. Okay. Now we have step 5. Step 6, as I hinted earlier, we'll establish two equations, two unknowns. But first, I'm going to say VB is also equal to, sorry, AB is also equal to AA plus alpha of AB as a vector cross RB from A. So now we're trying to find the velocity with respect by looking at the bar AB. That's the pink bar, perfectly vertical, perfectly horizontal. So let's get back to that. Minus omega squared of AB times R of B from A. Okay, we know the the left-hand side because we just found that in step 5. So I will write 0.2 alpha BC in the I direction plus 0.2 in the j direction. That's equal to what I found in step 4, which is AA. That is 0.4 in the I direction plus 0.4 in the j direction plus an unknown alpha again. So I will write that in terms of a scalar. So the magnitude of alpha AB in the k direction by assumption cross 0.3, which is 300 millimeters in the I direction. And from step 3 that I know, omega AB is 0, which results in this entire term being 0. So I don't have to write anything other than that. We will further expand this equation that we just got, simply that cross product, and we'll get everything the same on the left side. The first term remains the same, and we add simply 0.3 alpha AB in the j direction. Now we'll split the i's and j directions, so we have two equations and two unknowns. So the I direction will give me essentially 0.2 alpha BC. I don't need to write I anymore. Give me 0.4. And this is one equation, one unknown. So I can say alpha of BC magnitude is equal to 2 radians per second squared. If I put the vector sign on top, I can say this is 2 in the k directions radians per second squared. Now we'll still do the j direction. In j direction, I have 0.2. It's a constant. On the other side, 0.4 and plus 0.3 alpha AB. This is also one equation, one unknown, and it'll give me negative 0.2 over 0.3 is equal to alpha AB. So alpha AB's magnitude will be negative 2/3. Its vector will be negative 2/3 in the k direction, which is a clockwise rotation, and the units are in radians per second squared. All right, now we have step 6. We have two pieces of new information obtained, and we're on to our last step. Before I do that, let's go back to the question prompt and read the hint or suggestion they offered us. Consider the use of equation 6/3 with A as a moment center. I've pasted the picture of equation 6/3, and it says the sum of moment at a random point P is equal to um, the second moment of mass, sorry, times the angular acceleration of the bar that you want, times the uh, radius to the point, cross product, the net force at the point you want. Uh, it's, it's not the easiest thing to say by mouth, but it's quite easy to apply, so we'll get at it. Before that, I will just write the same equation down. So sum of moment at A is equal to alpha AB, because that's the bar we're looking at, times the second moment of mass at A of the bar plus R of, what is the R? Oh, rho. Rho is actually the distance to the center of mass from the point A. So I should technically write G/A as a vector, cross product, mass times the acceleration at A. So what do we do for summing up all the moments? So let's draw a free body diagram right here of bar AB. Now from statics, you can recall there's a tension here. There's another tension or reaction from the bar. And you have gravity acting at the center of mass, which is at G. The distance between them is 0.15 meters. Another 0.15 meters. So let's sum the moment about A. That means the force AO is not accounted for, and force of BC is our target, and that's the weight, which is equal to mg. So the sum of moment at A is equal to, and I would define counterclockwise as positive. So I get negative 0.15 as distance multiplied by 0.8 kilograms of mass times 9.81 of gravitational acceleration plus 0.3 meters distance multiplied by FCB as a tension by assumption. And that's the sum of moment. On the other end, I would drop the line, say I of A is equal to 1/3 ml squared. Because this is a uniform slender rod, by definition stated in the question, I can use this equation that you can look up on your table, and we could get 1/3 times the mass 0.8 kilograms multiply 0.3 squared length squared, and that will give us a number of 0.024 kilograms meter squared. I should probably call this a step 8 or step 7.5, but we can do this in one. It's simple enough. All right, so we'll write the equation again. We'll try to plug in all the numbers and we'll solve for FCB. So negative 0.15 times 0.8 times the gravity plus 0.3 FBC is equal to the other hand. Alpha of AB was negative 2/3 multiplied by the second moment of mass plus rho, which is actually just 0.15 because we're dropping the vector sign to make it simpler. That's the distance from A to G, so that distance, multiplied by the mass, 0.8 kilograms, and the acceleration, that is normal to the vector r of, G from A. That means we need to go up, and if you imagine the moment arm, if you have a parallel force or acceleration, well, then it won't create any moment. It will just create a tension, try to pull the thing apart, or a compression. Only when you have something perpendicular to the direction that you're interested would it create a rotation about it. So we're actually looking at the acceleration of A in the y direction, and I'll just use an arrow to point out that is from step 4, we found it's 0.4 meters per second squared. All right, so we'll skip the nasty math, and somehow you should arrive at the conclusion of 0.3 FCB is, oh, I did have some steps down, but show more steps, just avoid mistakes. Sometimes it's easy to troubleshoot if you have more steps down. Whoops. So after doing all the math, we found that the force in the bar BC is 4.031 newtons tensile. And that ends the question.